Hey, so in this video we're going to be working out the Gaussian integral, which is this integral over here, and it's a pretty important integral because it turns up quite often in statistics, especially in probability, because it represents the normal distribution. So if we want to just picture what the shape of the integral of the curve looks like, well, we know at x equals 0 it would cross the y-axis at y equals 1 because e to the 0 is 1. And we know as x gets bigger or smaller, the curve would tend to 0 because it's an exponential decay. So the shape of the graph would be like this. And what this integral is working out is the area under this graph, because it goes from x equals negative infinity to x equals positive infinity. So it's the total area enclosed between the x-axis over here and the function e to the minus x squared. So we're going to tackle this integral in what might seem like a convoluted way, but there is a method to my madness. So let's start by calling this integral I. So I is equal to the integral from negative infinity to infinity of e to the minus a x squared dx. And a is a real number. So because this is it's a definite integral because it has two limits. So this will work out to be some number. We know we could also write this integral in terms of another integration variable. So we could say this integral is also equal to the integral from negative infinity to infinity of e to the minus a y squared dy, because that's also equal to the same number. Because at the end of the day, this integral will just work out to be a number. So the trick which we're going to try is, let's consider I squared, which is the first integral, times by itself. But instead of writing out the same integral again, I'm just going to write it out in terms of y, and we'll see the reason behind that soon. So e to the minus a y squared dy. Now we've written out this product of integrals. We can rewrite this product as a double integral by moving the integral and the differentials around. So I squared is the same as the integral from negative infinity to infinity of the integral from negative infinity to infinity of e to the minus ax squared times e to the minus ay squared dx dy. So now we have a double integral, and what we notice is we're integrating x from negative infinity to infinity, and we're also integrating y from negative infinity to infinity. So if you think about it, we're really integrating over the entire xy plane, because the set of x values from negative infinity to infinity, well, that's just the entire x-axis, and the set of y values is from negative infinity to infinity is just the entire y-axis, and those two limits span out the entire xy plane. So the xy plane is just a plane of all pairs of real numbers. So in maths we call that object R2. So we can say that this integral is the double integral over R2 of e to the, we can tidy up the exponent a bit, and we could say e to the minus a x squared plus y squared dx dy. Now the x squared plus y squared in the exponent should look pretty Pythagoras-esque, or similar to the formula for the distance of a point on R2 from the origin. So that's sort of what we're going to be exploiting here. So if we do a coordinate transform from the current Cartesian coordinates, which is xy, to polar coordinates, which is r theta, we can simplify the integral a bit. So remember, in Cartesian coordinates, we map out a point using its distance from the y-axis, distance from the x-axis, which is its y-coordinate, and its distance from the y-axis, which is its x-coordinate, confusingly, to map out the point. In polar coordinates, instead of having an xy axis, we have this thing called the initial line, which is basically the positive x-axis, and we have this thing called the pole or the origin, and we mark out points using its distance from the pole, we call that r, and the angle it makes with the initial line, which we call theta. So using some basic trig and Pythagoras theorem, we could see that r squared is the same as x squared plus y squared, and x is equal to r cos theta, and y is r sine theta, which makes sense if you think about the right angle triangle, with this being y, x, and theta. So now if we change this integral over here into polar coordinates, it's pretty obvious that this exponent here is just r. So we can rewrite this integral as the double integral, and we're still integrating over r2, so that doesn't change, of e to the minus a. Now x squared plus y squared is r squared, and the differential we haven't changed yet. So for now it's dx dy. The reason why we're still integrating over r2 is we haven't changed the area we're integrating over. So we're still integrating over the entire xy plane, but we're just looking at it through a different lens, which is the polar coordinate system. So now we need to change this dx dy from Cartesian to polar. The way we'd go about that is, well, there's two ways actually. One is the geometric way, and one is the way using the Jacobian. So if we look at the geometric way first, dx dy represents a small change in x called dx, which I'm going to exaggerate a bit, times a small change in y, which I'm also exaggerating, called dy. And that gives you this little rectangular chunk of area called dA, which is a piece of r2, if you'd like to think about it that way. So let's try applying the same logic to polar coordinates. So here's our pole and our initial line. Say we start at this point and we change r a little bit. So let's increase r a bit to get dr. Again, I'm exaggerating this. And now let's increase theta a little bit to get d theta. So this gives out a little chunk of area shaped like that, dA. So in Cartesian coordinates, dA is dx dy, which is the chunk of area over here. In polar coordinates, dA isn't exactly dr d theta, but it's the area of this little shape, which we can assume to be a rectangle, because in reality this differential in area is so tiny, any curvature is not noticeable. It's the same reason behind how differentiation relies on the fact that when you zoom into a curve it's basically a straight line, or how the Earth's flat up close, but in reality it's like really curved. It's a geoid. So over here dA is, well, we know one side has length dr, the other side is basically an arc, so it has length r d theta. So dA transforms into r dr d theta. So that's what dx dy transforms into. Now this geometric method may seem really easy, but it won't exactly work for all coordinates. what that means is, say we're trying to transform between two different 5-dimensional coordinates, it'll be really hard to sketch out a little chunk of 5-dimensional volume. So in general cases, mathematicians came up with this method called the Jacobian. And the Jacobian is a second method which works for all coordinate transforms, and we can use this whenever we're able to express our current coordinate system, x and y, in terms of the new coordinate system. And we already know that how to express that, because x equals r cos theta and y is r sine theta. So what exactly is the Jacobian? Well, it's the determinant of a matrix called the Jacobian matrix. And the Jacobian matrix looks like this. J is, if we're transforming from xy to r theta, the Jacobian matrix would look like dx dr, that's an r, dx d theta, dy dr dy d theta. And no, I know how to write these. These are just curly d's because they represent partial derivatives. So a partial derivative is when you differentiate something with respect to just one of the variables and treat all other variables as constants. So we'll fill up this Jacobian matrix by calculating the partial derivatives. So we know that x is r cos theta, so dx dr is cos theta, and dx d theta, well, that's a differential, that's the derivative of r cos theta, which is minus r sine theta. Similarly for y, dy dr is sine theta, and the excuse me, dy d theta is r cos theta. Right? So now if we work out the determinant of the Jacobian, so that's the determinant of cos theta minus r sine theta and r cos theta. So the way we work our determinants of 2x2 matrices is we times these two, this and this, and we take away the product of these two, this and this. So that's cos theta times r cos theta, so that's r cos square theta minus sine theta times minus r sine theta, which is minus r sine square theta. So the negatives cancel and give a plus, so plus r sine square theta. And we can factor out the r, and using the trig identity, we know that cos square theta plus sine square theta is just 1. So the Jacobians are. So now how do we use the Jacobian to transform between coordinates? Well, the formula is we take the unit area in our initial coordinate system and we multiply that by the absolute value of the Jacobian times the differentials in our new coordinate system. So the absolute value of r is r dr d theta. In polar coordinates, we usually measure r as a positive number and theta as an angle going from 0 to 2 pi. So now we know what a Jacobian is. So both ways we found out what the differential is. So now, coming back to our double integral, I squared is equal to the double integral over r2 of e to the minus a r squared, and dx dy gets replaced by r dr d theta. So now you can probably see why we chose to switch the polar coordinates, because now instead of evaluating the integral e to the minus x squared, we have to evaluate r times e to the minus r squared, which is a much easier integral, as we'll soon see. The reason being is, well, first of all, we can rewrite this double integral as an iterated integral, which is a fancy way of saying an integral of an integral. So we're still integrating over R2. So now, but instead of R2 being from y equals minus infinity to y equals infinity, R2 is now from theta equals 0 to 2 pi, and r equals 0 to infinity, and the integral is r e to the minus a r squared dr, and we integrate that integral with respect to theta. So the reason why we didn't choose r from negative infinity to positive infinity is because if you think of the situation with the initial line, if you take r equals 0 to infinity, that's this entire ray, if you think about it, and then we're sweeping this ray 2 pi radians. So we're going to cover out the whole of R2. If we instead chose R going from negative infinity to infinity, we'd sweep out the area twice. So we could do that, but we'd have to change our theta angle to 0 to pi to avoid sweeping out the same area twice. So now that we know what the limits are, we can actually get to working out the integral. So I squared is the integral from 0 to 2 pi of theta times the integral from 0 to infinity of r times e to the minus a r squared dr, and then we integrate that with respect to theta. So what we notice here is that we could do integration by substitution to solve this first integral, or we could notice that e to the minus a r squared differentiates to itself times the derivative of the top bit, the exponent. So that's that times minus 2ar. So that means minus 1 over 2a e to the minus ar squared would differentiate to r e to the minus ar squared, which is our integrand. So using that, we can quickly work out the antiderivative of the expression we're integrating. Again, you could use integration by substitution, but sometimes spotting derivatives playing around is a bit quicker. So what we're going to evaluate is minus 1 over 2a times e to the minus a r squared from 0 to infinity d theta. And we could work out the integral, but a nice trick we can do is, because there's a negative sign here, we can swap the limits. So that's the integral from 0 to 2 pi of e to the minus a r squared divided by 2a from infinity to 0 d theta. So if we evaluate this at r equals 0, well, the top is just 1 over 2a, and the bottom, and when we plug in r is infinity, we get 0 because e to the minus infinity tends to 0. So that here is now 1 over 2a d theta. So 1 over 2a, well, a, remember, is a real number, so we're just integrating a constant. So that integrates to theta over 2a from 0 to 2 pi. And again, plug in theta equals 2 pi and plug in theta equals 0, you'd get, so 2 pi over 2a is just pi over a, times, subtract 0. So, and that's equal to pi over a. So that's I squared. So I, our original integral, is just the square root of that. So it is the square root of pi over a. So that means the integral from minus infinity to infinity of e to the minus a x squared dx is the square root of pi over a, which is a pretty interesting result if you think about it, because that means if we had to graph e to the minus x squared, the area it encloses with the x-axis is exactly equal to the square root of pi. And if you think about our double integral, if we were looking, because we were integrating over R2, if we were integrating e to the minus, say, r squared dr r dr d theta, well, e to the minus r squared, it would sort of look like a lump in 3 dimensions. That's a terrible lump, 1 second. It would sort of look like a lump in 3 dimensions. So it would have a shape something like that, and these are just concentric circles to just show its curvature. So it'll be like this lump bound by the surface, say z equals e to the minus r squared, and the entire xy plane R2, and that volume bound between these two surfaces would be exactly equal to pi, because I squared, if you remember, is equal to pi over a. So if a were 1, this volume would be exactly pi, which is a pretty cool result if you think about it. So yeah, that is your final answer. Hope you enjoyed this video. I had fun making it, and if you have ideas for any more videos or any other problems you want me to solve, drop a comment below, and until then, see you next time.